Hello friends, that is my second lecture on Maxwell equation. So in this lecture, I'm going to cover Maxwell first equation and Maxwell second. Before I start of my the lecture, I request you to please like and share my video. Then, so the Maxwell first equation. Maxwell first equation is actually the Gauss law, that is also called the Gauss law of electricity. And as per the statement of the Gauss law, the total electric flux, that is represented as the phi, passing through any closed surface is equal to the total charge enclosed by that surface. See this particular diagram where a charge is represented by the plus sign and the electric lines of fields is moving outside the surface. We choose a circle here, so that is basically it represents a cylindrical surface that is called the Gaussian surface, and charge is moving outside direction due to the positive charge, because if you know that a positive electric fields start from the positive charge and end either through the negative charge or at infinite. Similarly, the direction of this electric lines of field is negative in the case of the negative charges put at the center. So, as per the statement of the Gauss law, the phi is equal to the Q enclosed, where phi is the flux and Q enclosed is the total charge enclosed by this Gaussian surface shown in the figure. The surface are the any type, but it must be the symmetric. Then the phi is also represented as the integral of dds, where d is the electric flux density. And similarly, the charge enclosed is represented as the volume charge density rho v multiplied by dv. So the Q enclosed is integral of rho v dv, and the phi is equal to integral of dds. So the integral of dds is equal to the integral of the rho v dv. Left hand side is basically a surface integral and right hand side is the volume integral. That is called the Maxwell first equation, or Maxwell equation in integral form, or Maxwell equation derived from the Gauss law. Then, if you want to calculate this particular Maxwell equation in a differential form, then we use the divergence theorem. So divergence theorem basically describe the relationship between the surface integral and volume integral. As per the divergence theorem, integral of the ds is equal to the integral of the divergence of d into dv. So by using this particular theorem, integral of rho v dv is equal to integral of del dot d dv. We see here that the volume integral in the left side and the right side. So if you remove this by volume integral, then we got del dot d equal to rho v. Sorry, I'm forget to put the dot between del dot d. That is called basically the Maxwell first equation, and it is represented in the differential form, and it's represent volume charge density in a medium is equal to the divergence of electric flux density in that medium, because the flux density is always defined in a particular medium. That's why we represent, and the del dot d is the divergence. So the divergence of the electric flux density in a medium is equal to the volume charge density in that medium. So basically the Gauss law is the alternative statement of the Coulomb's law. Coulomb's law is a general law where we can calculate a force between the two charges, and then we calculate the electric field. But in the case of symmetrical charge distribution, we use Gauss law to calculate electric field intensity. Then that is all about the Maxwell first equation. Then we move to the Maxwell third equation. So we have know that a potential difference between a points A and B is represented as VAB is independent of the path taken. So in the case of the closed path, VAB and VBA just depends upon the direction. So if VAB is positive, VBA is negative, and either the VAB is positive or negative, it simple means that either the loss of potential or gain in the potential. So the negative sign indicate the loss of potential and positive sign indicate the gain in potential. So in the closed path, we can easily write VAB is equal to minus VBA. It means VAB plus VBA is equal to 0. And similarly, if VAB and VBA is also written as integral of E dot dl, it means integral of E dot dl is the equal to the 0. And E dot dl is, why we write E dot dl? Because V equal to E into D. It means the line integral of electric field along a closed path is 0. That is called the Maxwell third equation. It is an integral form. Then again we derive this Maxwell equation in the differential form. One more thing. So if the integral of EDL is equal to 0, it also means that no work is done in moving a charge along a closed path in an electrostatic environment. So that is the basically the conclusion of the Maxwell third equation. Then for Maxwell equation in a differential form, we use Stokes theorem. So Stokes theorem nothing but it shows the relationship between the line integral and the surface integral. So as per Stokes theorem, the line integral of E dot dl is equal to the surface integral of the del cross E. So by using the equation 1 and 2, we can write integral of del cross E dot ds equal to 0. So we remove this integral sign, then it becomes del cross E is equal to 0. Del cross is nothing but the curl of the electric field intensity, and it is called as the Maxwell third equation. And it is also called Maxwell third equation in the differential form. So del cross E is nothing but the curl of the electric field, is so that in the electric field having a conservative nature. So that is the basically the Maxwell third equation in the static cases. But this particular Maxwell equation is also derived for the dynamic or the time varying cases. So this particular equation is valid for the static case, but for dynamic and time varying case, the above equation must be modified. So it is must be modified, and we use a Faraday law. So basically, as per the Faraday statement, a static magnetic field produces no current, but a time varying field produces an induced voltage in a closed circuit which causes a flow of current. That is the basically the Faraday experiment. And in terms of the Faraday law, the induced EMF, that is represented as VEMF, in any closed circuit is equal to the time rate of charge of the magnetic flux linkage by this particular circuit. See this particular circuit where we created a coil that is connected with a galvanometer, and second a magnet. We just come close to this particular circuit, so that there are the magnetic lines of the field that is interact with this particular the coil. So this due to that magnetic linkage to the coil, a VMF is or a EMF is introduced in the particular coil. So that is the Faraday law in represented. So we call is VMF is equal to minus d phi upon dt. That is nothing but the same equation. Induced EMF is equal to the time rate of the magnetic flux. So basically here the del phi is nothing but the magnetic flux, not the electric flux. And we know that the VMF is integral of E dot dl. And similarly, as per the Gauss law of the magnetism, phi is integral of B dot ds, where B is the magnetic flux density, similar to the D, that where the D is called the electric flux density. Then again we put this into the equation. Then minus d phi of d phi upon dt is equal to minus del upon del t integral of B dot ds. And then by when we put these equation in the equation 3, then integral of E dot dl is equal to the minus del upon del t integral of b dot ds. That is basically the Maxwell equation in integral form. We also interchange the differential and integral position, then it's become symmetry. So at that case, the integral of d dot dl is equal to the minus of the integral of del b upon del t dot ds. It is just we can interchange the position of integral and the differential. Then that is basically the Maxwell equation in the integral form in the case of the Maxwell third equation. So it is basically the Maxwell third equation in integral form for the time varying cases. So again, we can calculate this Maxwell equation in a differential form for the time varying cases. So we use Stokes theorem. Again, integral of E dot dl is equal to the surface integral of del cross E ds. Then by 6 into the 7, we can remove the integral of, replace integral of E dot dl is equal to the surface integral of del cross E dot ds. Then they have the both the side, they have the surface integral. It means the del cross E is minus del B upon del T. That is called the Maxwell equation in differential form. Maxwell third equation are the Maxwell equation derived from the Faraday law, and it's so that for the time varying case electric field is not conservative, but in the static case electric field is conservative in the nature. That is all about the Maxwell first and Maxwell third equation. So in this lecture I am covering the Maxwell first equation, then the Maxwell third equation, and the Maxwell third equation is modified in the case of the time varying cases. It means we have discussed Maxwell third equation for the static case and Maxwell third equation for time varying case also. Thanks for your attention. I'm again request you to please like and share my video. Thanks for your attention.